Welcome back to a new video. So in this video, I will introduce leaky confined aquifers in their transient form. So when we start pumping, we do a pumping test and we look at drawdown over time and what happens if the confined aquifer is semi-confined, meaning there's some leakage from another aquifer. So again, a reminder from our previous modules, previous course, about what a semi-confined aquifer is, right? It's a confined aquifer where there is some semi-impervious layer at the top, an aquitard as opposed to an aquifuge, right? Something that lets some water trickle down from an aquifer that's on top, right? So it could be, for example, an unconfined aquifer on the top here, a or an aquitard, so some impervious layer, but that's not completely impervious, it lets some water go. And then finally our confined aquifer where we're pumping into down here, right? So as we pump, some water will come from that top aquifer and recharge our confined aquifer. So the question to you is, what do we expect would happen, right? If we remember from the Theis curve, right? For a confined aquifer, we have drawdown versus time. And things look like this. Well, that should be log drawdown versus log time, if we remember from our previous lecture. So now if we have a recharge, so this is for a completely confined case, right? So now let's think about what happens in a semi-confined case. Well, at the beginning, right, we still have the same compressibility, or the matrix of the aquifer is the same. So when you turn on the pump, so at the very beginning, you would expect something similar to happen, but as you pump over time, now we have, lower pressures, right? We're pumping into that aquifer, so we're basically doing a vacuum, and now we're expecting some water coming from our unconfined or our surface aquifer to recharge that aquifer. So what happens when this happens, right? When there's more water coming in, like there's a recharge boundary, well then all of a sudden our drawdown drops slower, right? So we would expect the drawdown, the water level in the well pretty much to start dropping slower because there's more water available for that same pumping rate. What that means that now we're starting to diverge from our Theis curve. Again, this is Theis here for a straight confine, and we start to diverge because again we have more water available. So for the same pumping, right, we don't drop the water in the well as fast. To the point where at some point we would expect some sort of an equilibrium, right? When the vacuuming from the pump is compensated by the recharge boundary or by the leakage, from another aquifer, then at some point we would expect some complete equilibrium between those two processes, meaning, right, we would expect when there's complete equilibrium, basically the drawdown is steady, right? The pump, whatever you pump out is recharged by the top aquifer, so there's no change in the water level in the well at that point. So this is really what we would expect for a leaky confined aquifer. Okay. Now here are the equations. So what happens is now we'll have an extra term in our Wells function. So let me first go back to the fundamental equation, right? So we still have that time differential. Obviously, we're still in the transient equation, transient case, so we have that time differential. But now we have also that leakage rate, and if you remember again from our first course on flow equations, the leakage rate, we can basically write the Darcy flux or Darcy's equation, right, for that for that aquitard, or for that semi-impervious layer. So we can write that flux, that water flux, from Darcy's equation, and again that would be the hydraulic conductivity of that of that aquitard times basically its thickness, so the head on top and the bottom, divided by its thickness. So this is just the Darcy equation for that exact aquitard that we've seen before. Okay, so in radial coordinates, right, we can write it this way, and of course in terms of drawdown instead of head, right, we just change the signs. Again, this is minus drawdown, so now we have a sign that changed. So all of this is the same as before. So now we can write this equation as drawdown instead of head. So everything is pretty standard. It's just, you know, a review of what equations are we talking about here. Okay, now here's the new part, if you will, for this method. So now we have a new Wells function that has two different parameters. Remember, the Wells function for the confined aquifer was just W of U, right? There was just that one U argument in that function. Well, now we'll have a family of curves that have U and then R over B as a second argument. So we'll have a family of curve. Now the good thing is now we can read, you know, again, we can read from our type curve the arguments that we need, right? And then we can finally find all we need, which is again the storativity, the transmissivity, and now we'll also have, with some, you know, caveats that I'll show in a second, but we can also find the properties of the aquitard leaking into that confined aquifer, right? So the Artisan well function, we call it sometimes, so it's just another, you know, well function, but it's nice, the Artisan Wells function, and we can look it up, obviously. I mean, it's tabulated in your book, in the Feder book. You can find it tabulated at the end. Here, I just use it in MATLAB or in Excel. I'll show you some Excel examples in a second. Or in MATLAB, you can just like plot it, and this is what they look like, okay? So again, you can see here that second argument, R over B. So here's a whole family of R over B values, and you can see that basically you traverse, right, a whole family of curves up to the Thies curve on the top here. So this is still our typical confined, right, that top one here. The top one is just the Thies curve, just the exact same as a completely confined aquifer, and you can see, of course, if R over B equals 0, well, basically we just have, you know, a confined aquifer. And then as R over B increases down, now we're going this way, you know, there's more and more leakage, if you will, so sooner and sooner we reach that equilibrium because there's more and more water coming into our confined aquifer and compensating for our pumping. Okay, so this is really how you should read this thing. And again, the principle of using those graphical methods or type curves is again to line up your data. So here the dots are, you know, some data. Line them up with a curve. So this is where it becomes a little tricky to use it by hand because you sort of have to make a judgment, right? Now on the left-hand side, you can see how all those curves are pretty much, you know, on top of one another. So when you want to fit by eye, if you will, your data in the curves, you know, it becomes a little tricky. So here, you know, it's a pretty good example, but real data is often a little bit more noisy, and sometimes it's not very easy to pick, you know, which curve precisely is the right curve. But this is still, you know, the method, basically. This is how you do it. So again, you find the right curve, you fit it, and now, of course, you still have a match point that you can choose at 1 and 1, but in this case, I didn't. So here you can see that the value of 1 over u here on the x-axis is here, and the value of wu is here, and r over b, now this is that orange curve, so if we start from the bottom, let's say, we go to the orange curve, so it looks like a 0.3 probably, between the yellow and the blue, yes, 0.3. So now we have the value of 1 over u, the value of wu, the value of r over b, the value of time, and the value of drawdown, right? So now we have everything we need, we can just plug it in. So that's how you get all those values. I will show you in the next video, I will go back through this example and we'll do the reading and, you know, finding the aquifer properties for a semi-confined aquifer. Thank you.